I'm back, and so just before the break, I was trying to show you how do we estimate or draw the snow drift diagram for a second reason, which is multi-level, higher roof next to a lower roof. Now, as I said before the break, is that this is we start from here, and you can see there are a couple of factors we need to know before we find the drift diagram. And to be specific, we need to find the value of capital F and then capital beta, or sorry, not capital, it's beta, just beta. Okay. So guys, there's a discussion which is called the source. When the snow accumulates at the lower roof, what is the source of the accumulation? So you can see on my screen there is some graphics, and the graphics assembly, it's a cut and paste from the code, the Alberta Building Code, and this shows you the different sources of accumulation. Okay, so I want you guys to look at the far left one, the far left one. So the far left one, it is called case I or case 1, and you can see there is a hatched, like a hatched or grade area on the roof, and it's called upper roof. So the upper roof is, in case number I, is the source. And you can see when the upper roof is the source and the wind blows from up down or from front to the back, then you can see there is an area where it's marked as lower snow, like snow drift. So, you know, this case number I, it means the upper roof is the source of the accumulation. Now, when we go to case number 2 in the middle, the same place, we're talking about the snow drift in the same place. However, in case number 2, the area which is shaded on the lower roof is the source of accumulation. And please look at the wind direction. So in every one of those cases, there is a wind direction. Broji, do you have a question?
Yeah, I'm just looking at case 1 there with the wind. Why wouldn't the snowdrift be on the top side of the upper roof? Assuming that that's like a similar corner.
Your question is why the drift is not on the upper roof?
Why is it not on the other side of the upper roof, on the wind side of the upper roof?
Because the wind is blowing, it will be on the leeward side of the building, right? So the wind will take some snow off the upper roof, and then it will make a drift on this side, on the other side. It
Okay.
will blow off some of the snow on the top, on the upper roof, then it blow it down to the lower roof.
Okay,
Okay.
that makes sense.
On case number 2, the wind changes its direction, so it is blowing from below up or from front to the back, and then in this case, the source of the accumulation on the same area. So the area is the same, by the way, and so but the source is different. The source right now is not the upper roof. The wind will hit the lower roof portion, which is currently shaded, and then will cause accumulation wherever shown. Now the last part, if the wind comes to an angle, so you can see on the case number 3, the wind comes on an angle like 45 degrees, and it will take some snow off the lower roof, and it will do some accumulation on the same area. Okay, so guys, really what I want to take from this discussion is source, the word source. By the way, this discussion is kind of brand new, so I can tell you back in 2010, what I'm discussing right now does not exist. It was very simple. There's a very simple formula. However, probably there was some research on how to find the snow, and they said, okay, let's come up with the source and refine our procedure to find the snow on a multi-level. Okay, so again, all I want you to understand from this picture is what is the source. The source can be the upper roof, or it can be different portion on the lower roof. Okay, Now, again, until the end of the class, I guess you will get better idea about the source, but please be patient. And this is something I will always ask you, be patient. Don't give up on me, okay? Be patient. Now, once we know the source, whether it's upper roof or different portion of the lower roof on case 1 or 2 or case number 3, next is, here is the equation that we will use to find the F, okay? So one more time, if you remember, the CA of 0 was the lesser of those numbers, so beta, gamma, H, CB, SS, and F divided by CB. Now, I know you will ask, okay, what's beta or how much is beta? Here we go. Beta is equal to 1 for case 1, which is if the source is the upper roof, and is equal to 0.67 for case number 2 or case number 3, where the source of the accumulation is portion of the lower roof. Okay? H is the difference in elevation between the lower roof surface and the top of the parapet, as Brody said. So that's what you, Brody, said, huh? The H, which is shown on the section already. Now, what is the F? Without going into so much detail, there is an empirical equation that finds for you the F. Really, what I want you to focus is this. The F, the maximum value is 5. The maximum value is 5. So which means if you find the F more than 5, then what can you do? When I do the estimate for F and F is equal to 6, then don't use 6, maximum 5, so use 5. If F comes out to be 3, great, you will take it. 4, yes, you can take it. 4.9, yes, you can take it. 5, you can take it. 5.1, no, F is maximum is 5. Please take a note, and you will see that in the example. Now, part of the calculation of F, you can see beta here is one more time here. So beta is something you know. Gamma is the specific weight of the snow. And then you will see there is something called L sub CS. So in my class so far, you know what is L sub C. Let me check. What is L sub C? Show your hands if you know the answer. What is L sub C? Anybody is following what is L sub C? Don't go into the slides. Tell me what is L sub C. Okay, fine. So L sub C is the characteristic length of your roof. Okay, which means it's just function of the width and the length of your roof. And here it's not L sub C, it is L sub C S for the source. So the L sub C is the characteristic length of the source. So if the source is the higher roof, then we use the dimensions of the higher roof. In case number 2, there is one portion of the lower roof is the source, so we use those dimensions. In case number 3, there is another portion of the lower roof, which is the source, then we take the dimensions of this area of the lower roof. Again, if you don't follow, okay, fine, just be patient, because at the end of this class, I have numerical example that's supposed to clear all the confusion. But L sub CS is the characteristic length of the source, depending on what is the source, whether in case I or case double I or triple I. Okay, let's move on. Now here is another like kind of cap. The beta, as we said, the cap is equal to 1 in case I, where the higher roof is the source, and is equal to 0.67 in case 2 and 3, where the lower roof is the source of the accumulation. Also, guys, if you go back in the equation, you will see this equation here has a minus 5 HB dash. And some of you will say, okay, Tahir, we don't know what is HB dash. If you go back to the sketch, it says HB here. HB is the height of the parapet. So what is HB dash? It is simply in the next slide, and HB dash is connected to the HB. It's kind of, you think about it as a modified height of the parapet. and you can see the HB dash is equal to HP minus 0.8 SS divided by gamma, and it has to be in between the zero, so it has to be more than zero, and it has to be less than LCS over 5. Guys, please take a note. Whenever there is a condition, after you estimate something, you have to make sure that the condition is happening. Let me ask you, what if you estimate the height of the parapet dash, like HB dash, and it is minus 0.1 or minus 0.3? Then what you should do? My question is, what if during the estimate of HB dash, you found HB dash to be minus 0.3? I'm asking you.
That's not
What
possible.
can you do? Huh?
That's not possible. The parapet can't be smaller.
I understand, but remember that HB can be a zero. Huh? Look at the equation. H sub P can be zero if your building has no parapet. Like for example, if you go to the sketch, let me show you the cross section. So this cross section, guys, this cross section here on the top graphics, the higher roof has a parapet. How about the lower roof? It doesn't have any parapet, which means HP sometimes can be zero if there is no parapet. I'm asking you, look at this equation. If HB has no parapet, so it means zero, it means HB dash is equal to negative, correct? And look at this equation. It tells you minimum is zero, maximum is LS over 5 or LCS over 5. What I'm saying here is, if you find out that this number is negative, no, you have to use zero. And if it exceeds this number, let's say LCS is equal to 20. So 20 over 5, that's 4. If your HB dash is less than 4, great. If it's more than 4, then you need to stick to this condition and use 4 as a maximum. Are you following? I need to hear your voice. Are you following?
Sir?
Yes.
Go ahead, Jelly.
Say it again. Your H prime P should have a maximum of 4 or 5.
It is not number. It is in the equation. Do you see my screen?
Yeah.
Do you see my slide? Next to where you estimate the H prime P, there is a condition. It says but 0, like H prime P should be more than equal 0 and less than LCS over 5. Do you see that?
Yeah, I know. Your question before is what happened if it's negative, then you're going to take 0. That's right.
Yeah, and if it exceeds LCS over 5, then use LCS over 5.
Oh, yeah. So that is your maximum.
Yes.
Yeah, thank you.
No problem. Okay, guys, now you can see, I know so far things are not easy, but I'm going to show you when we do the actual calculations, it will be way easier. Before I finish this slide, need to remind you, what is HB? Simply HP, it is connected again to the source. So in case number I, the HP is simply the height of the parapet on the upper roof. And in case number 2 and number 3, the HB in this equation will be the parapet of the lower, since the lower in case number 2 and number 3, the lower is the source of the accumulation. Also for the calculation of L sub CS, then it's equal to 2W minus W squared over L. And remember, this is for the source. So in case number 1, the source is the higher roof, and that's why I need to use the dimensions of the higher roof. In case number 2 and number 3, they are different areas of the lower roof, and we need to use those dimensions to figure the L sub CS. Okay. Last but not least, now you can see, Tahir, now we are in the process of estimating the values, and looks like there are 3 cases. Which one should I do? Should I perform a calculation based on case number 1 or number 2 or number 3, or I should do all of them? The answer is, any help?
I guess depends on the direction of your roof. I mean, of the wind into your roof.
Yeah, that's true. Case 1 and case 2 and case number 3 is function of where the wind blows. But the thing is, wind, yes, it has a dominating direction in the year, but it can blow from any direction. It can change its direction, okay? And that's why, because wind can blow from any direction. Now the answer is?
All of them.
Thank you, sir. That's correct. Because simply we have no control where the wind can blow, then we have to re-estimate the whole thing 3 times. One time based on case number 1 assumption, and number 2, and then number 3. And then what should we do at the very end? Read statement number 4. So on statement number 4, which I boxed this one out in red, the value of CA of 0 shall be the highest of case 1, case 2, case 3, considering the different roof sources, area, drifting snow. So guys, here is the answer. It means in our calculations, what we should do is we should simply perform a calculation 3 times for case number 1, where the source of the accumulation is the higher roof. One more time for case number 2, where the source of the accumulation is part of the lower roof, and case number 3, where another part of the lower roof is the source of the accumulation. Then when we find for every single case, we will end up with value called A sub 0. What should be my A sub 0 in my design? It should be, CA of 0, which means accumulation factor at distance 0. So finally, what you have to do is you choose the maximum out the 3 values from every case. Okay, I know things right now is not easy. Oh my God, it's just like too much, it's difficult. So let me show you an example. So guys, here is a 3D, and hopefully this picture is better than what provided by the code. I kind of built a quick Revit model to try to show you my idea. So you can see this a 3D picture of a building, and you can see it has just like one main floor and then a second floor, but the second floor doesn't occupy the entire area of the building. You can see, and then on the top of the high roof, there is a parapet going around. Okay. So this is the 3D picture, and then I'm going to show you the plan view. So here we go. Here is the plan view and the cross section of the same building. So whatever you see here in 3D, there is a cross section and plan view for this building. Okay, now dimensions are given. I want you guys to take a minute and look at the dimensions. So the building is 18 meter by, I guess, 24. 18 by 24. Look at the grid lines on the left side. So we have 4 times 6, so that's 24 meter. And then we have 8 and 10, those are 18. Remember, those dimensions are in millimeters. Okay. Next is, I want you guys to look at the section. So I cut section through the building, and you can see here, again, we have main floor, and we have a second floor, and we have a third floor. You can see elevation. So the elevation of the main floor is 0. The elevation of the second floor is 1,000, and the elevation of the third floor, the elevation of the second floor is 5,000, and the elevation of the third floor is 8,000. And then finally, I put here between grid line 2 and grid line 3. I'm not sure, it's not very clear on my screen, but probably when you download the file, you will see it better. Okay, so there is a spot elevation which I added between 2 and 3. Anybody can see this number? Are you able to see the spot elevation that I added between grid line 2 and 3 on the elevation?
Yes.
How much?
9,200. Yeah.
I cannot see it. Maybe I need my glasses, but I cannot see it very well. But here we go. So let me ask you, what is the parapet height on the lower roof? Any help?
There is no parapet
height on the lower roof.
There is no parapet.
Meters. 200.
And what does it mean mathematically? What's the parapet height on the lower roof?
0.
Thank you, sir. How about the parapet height on the higher roof?
200.
No.
1.2 meters.
1.2 meter. Look at the elevation. So on the top of the parapet is 9,200, and then the floor of the third floor is simply 8,000. So if you subtract the two numbers, it means parapet height is 1,200 millimeters. So 1.2 meter.
That number looks like 8,200, not 9,200.
No, it is 92.
Okay, I can't
My
see
friend,
that.
I cannot see. That's why I ask you. I cannot see. So it is 9,200, and the parapet height on the higher roof is 1,200 millimeter. Now,
Yep.
okay, now guys, so now we know the dimension, we know the geometry of the building, and it says office building in Calgary. By the way, office building Calgary, those are two different things. Office building in Calgary, those are two different things. In Calgary, it will dictate the SS and SR, and office building, it will dictate the occupancy and the importance factor of this building. Okay, so let's move on to the solution. But before we do that, guys, the whole calculations, and I think this will be probably for the next 10 minutes or so. Really, what we're trying to do is this. We're trying to, you see the diagram, load diagram of my cross section in two colors? Do you see the load diagrams in two colors in my section? Really, my objective from now until we finish this problem is to simply find the snow drift diagram on the lower roof. But I want to say something which is very important. You will see we will do a lot of calculations, but guess what? All the calculations will only focus on the lower roof. Let me ask you, do you see anywhere else on the cross section that we will get accumulation? Do you see?
Yes.
Do you
on
see
the back.
anywhere on my cross section that is not the multi-level? So for sure, what I show you right now is the multi-level or drift due to multi-level. The diagram is in, I think it's sort of a reddish something and it's yellowish. Okay, this is the snow load diagram on the lower roof, and you can see there is accumulation. Why there is accumulation is because the multi-level, there is a higher roof and lower roof, and they are adjacent to each other. My question is there anywhere else on the same building, on the same cross section, that we anticipate snow drift?
Okay.
Okay, I'll go to the 3D. I'll go to the 3D one more time. Okay, guys. So again, this is a 3D picture. There is a higher roof, lower roof. So which means on the lower roof, there will be a drift. But do you see any? Diego, thank you. So Diego is saying on the upper level. That is correct. Guys, please take a moment and you can see on the upper roof, there is a parapet around, and parapet is one of the reasons that is called the roof projection, and it will cause some accumulation. Really, what I'm trying to say here is, and I'm trying to emphasize is, students, after they estimate hundreds of numbers, they kind of lost. They don't know where to place them, okay? So when I'm done today, like let's say after 10 minutes, you will see I only figure out the drift due to multi-level. However, in this example, I'm not showing you the snow drift on the higher roof due to parapet. If you want to do it, it's not very difficult. You just have to go back a couple of slides, like to this slide here, like this slide here, and this tells you how to find the snow accumulation from the parapet on the higher roof. Hopefully this is clear, and hopefully nobody is lost. I know it's a long process, but please know that all our calculation going forward, it focuses only on the snow diagram on the lower roof. However, if you want to draw the diagram on the top roof, then it's a different business. Okay, now let me show you. So you can see here, I'm going to do all the cases, and I'm starting here with case number 1. I'm not sure if it says, yeah, it says here case number 1. Okay, so but let me do it step by step. Number 1, you say, here is my building, it's in Calgary, so which means SS and SR is 1.1 and 0.1. Hopefully by now you guys remember those numbers. SS is 1.1, SR is 0.1, both are in KBAs. Next is office building. Office building, it's just a normal importance. It's not police station, it's not power station, it's not post disaster, so it's normal importance. And the IS is equal to 1, just 1, okay? And then there is a calculation which is not really related to any case, which is the specific weight of the snow. So without details, I mentioned here, I said Gamma is equal to 2.67. Hopefully, guys, you remember how Tahir got this number, 2.67. Okay, this is the snow specific weight in Calgary because the SS in Calgary is 1.1, and since it's less than 4, great, so 2.67. Now let me show you step by step on how to do the calculation, but I'm not going to focus right now. I will just go back and show you the big picture. So guys, look at the math again. So watch this, please. You can see to find the XD, I need CA of 0. Do you agree? If I want to find XD, I need CA of 0. Do you guys agree?
Yes.
Thank you. And you can see here is CA of 0. So in order for me to find CA of 0, obviously, everything is known except F and beta, which means, oh, I need to find my F and beta. So beta is easy. It depends on the case. Case number 1, beta is equal to 1. And case number 2 and 3, beta is equal to 0.67. But obviously, F is a problem. I need to find F. Next is, how much is my F? You can see the F comes from this equation. However, to find the F, then I need to find my HB dash. Okay, so you can see I go here, I find my HB dash. So guys, the conclusion is, and if you're following the discussion, guys, that's enough. Muhammad, I think you have a problem with your internet. Okay. Now, guys, look at this. How we do the math. Obviously, we have to do the math backwards. And what does it mean? It means I have to find HB dash first. When I know my HB dash, what I do is I go find my F. And when I know my F, I go find my CA of 0. So all I'm trying to say here is, although the equations are listed in one order, but when we simply push the parameters, we have to do the equations in a reverse fashion. So we have to do HB dash first, then F, and then finally C of 0. Look up my numerical example and let's see. Okay, here we go. Okay, so you can see here, I'm starting with case number 1, and I'm saying, I'm very clear, I said here, high roof is the source of the accumulation or source of the drift. And on the sketch to the right, I kind of highlighted and shaded the source. I write here, remember that's the source. In red, there is a source. So high roof is the source. Now, guys, look at this. We know that as soon as we say the high roof is the source, then beta is equal to 1. Beta equal to 1. Also, since you said the high roof is the source, then let's find what are the dimensions of the high roof. Okay? So guys, probably this is too small. So I will remind you, if I go back here, what the high roof is here. The high roof is between grid line A and B and grid line 1 and 3. This is the high roof between 1 and 3 and A and B. So the dimensions of the high roof is 12 meter, 6 plus 6, multiplied by 8 meter. So the length of the high roof is 12 meter and the width is 8 meter, which will yield to the following. So you know the LS and you know the WS, 12 and 8. So you can find the L sub CS. Very simple. 2 times 8 minus 8 squared divided by 12, you get 10.67. So here is your LCS. Guys, I'm sorry, probably I need to change this one. Oh, sorry, it's here, it's correct. It's LCS. It's 10.67. Then once you know the L sub CS, then you go find your HB dash. HB dash is equal to HP, which is the height of the parapet on the top of the source, which is 1.2 meter, which is 9.2 meter minus 8. Then minus 0.8 times SS divided by gamma. So we get 0.87. Remember, in red here, what I did is I simply put the check. You must make sure that 0.87 is somewhere between the 0, so it's more than 0, and less than LCS divided by 5, which is happening already. So I said, okay, so we are going to take the HB dash as is. One more time to remind you, if HB dash is less than 0, so use 0. If HB dash is more than 10.67 divided by 5, then we use this number as maximum. Then finally, once you find H prime B, then you find your F. So F is equal this math here, and then is equal to 2.17 less than 5, so it's okay. So you can see I kind of put the check here in red because I want to warn you. Most of my students, when you do the calculation, they totally forget about the condition or the check. Please don't forget the check, okay? Now, finally, once we know the F, we can find the CA of 0 by finding two numbers, the lesser of this number and this number, and here we go, 2.71. So the CA of 0 is equal to 2.71. Remember, this is case number 1, case I. We're not finished yet. So we figure out the accumulation factor next to the higher roof for case number 1. So what we have to do is we have to repeat the whole thing again for case number 2. Let me show you. So in case number 2, you can see, look at the shaded area. So the shaded area is the source of the accumulation. And it's on the lower roof. Let's get the dimensions. So dimension, let's go back here to this slide here. Dimension in this case will be 12 times 18. I'm not sure if you agree on that. So in case number 2, where the lower portion of the lower roof is the source, then in this case, it is 12 by 18. You can see that very clear here. So the beta, because case number 2, beta is equal to 0.67. LS is 18, WS is 12, and you can find the characteristic length of the source, which will be 16 meter. Remember, 16 is in between 18 and 12. Okay? If you do anything else, it means you've done a mistake. L sub C S should be anywhere between LS and WS. The next is you need to find H prime P, and H prime B is connected to the HP, and remember HP is the height of the parapet on the source. In case number 2, the source is the lower roof, and if you look at my 3D, I'll go back to my 3D. So you can see here my 3D looks like the lower roof doesn't have any parapet, which means HP is equal to 0, and if HP is equal to 0, it means 0 minus 0.8, and like I said before, you can see we end up with a negative value of H prime P. Remember, in red here, I did the check, and since it's less than 0, I'm going to use H prime P in the future calculation as 0. So here we go. You can see F is equal to, and I'm writing the math, and here we go. The 0 is here of H prime P, and then ended up with F equal 2.26. Less than 5, so it's okay. And then what we do next is we figure out the CA of 0, we estimate two numbers, and then we figure the CA of 0. So far, we have two values of CA of 0, two values so far. I'm not finished yet. I'm going to go ahead to case number 3. Case number 3, and you can see the difference. Case number 3 is this area here is the source of the accumulation, where the beta is still 0.67. However, you have to find the new dimensions for the area of accumulation or the source, which is from the dimension of the building. It is 12 by 10. You find the characteristic length, which will be in between. It is 11.67, which is in between 10 and 12. Great. Then next is you figure the H prime P. Remember, on the lower roof, the parapet height is equal to 0. So what does it mean? It means your H prime P is equal to negative value, which is still the same as case number 2. The H prime B is equal to 0. Then you continue and you find a new value for the F. And based on the F, you find a new value for the CA of 0. Okay, so far, guys, we have 3 values of CA of 0. 3 values, not only one. CA of 0 from case number 1. From case number 2, case number 3. And the code says, and I will remind you where the code. So the code says you need to use the maximum out of those. I'll go back. So on this slide, guys, on statement number 4, it says the value of CA of 0 shall be the highest of case 1, 2, and 3. So which means all I have to do is Here we have here a 2.71 from case number 1, 2.83 from case number 2, and then finally 2.56 from case number 3. So which means your CA of 0 is equal to 2.83 as a maximum of the 3 of them. Very important, it is unitless. This is not a load intensity. CA of 0 is not load intensity, it's not in kVA. It is accumulation factor at distance 0 from the high roof. So what should we do next to find the snow intensity close to or next to the high roof? Very, very simple. What you have to do is you go to your snow equation, and simply you replace the one. Typically, it's like away from your high roof. After distance xd, the accumulation factor is equal to 1. You can see here I have 2 equations. So look at my screen. I have 2 numbers, S0 and SXD. What are those numbers? Those are the snow load intensity at 2 different distances. Number 1 is 0. It means next to the high roof. And then the other one is at distance xd when the snow drift ends, okay, where the CA of 0 is equal to 1. You will see the 2 equations are identical. So the importance factor is the same as the importance factor. The 1.1 is the same, 0.8 is the same, everything is the same except the CA of 0. Please watch this. So at distance 0 from the high roof, it is 2.83, and then after xd, then it became 1. So guys, look at this now. I got a snow intensity, which is 2.59 kVA, and then 0.98, which is approximately 1 kVA. So if you want to put back those numbers on your elevation, what you will see is, you will see I'm sorry guys, I have to finish. After you find CA of 0, we can find xd now, only now. Remember, if I go back to this slide here, you can see the xd, you can find it only after you find CA of 0. So once we have figured already our CA of 0 equal 2.83, then I can put it back in this equation. I can find xd in meter. Here we go. So you can see my xd is equal to 3 meter. My drift distance is equal to 3 meter. So the snow drift will end after 3 meter. How about the load intensity? Next to your high roof is 2.59. After 3 meter, it goes back to 1, which is the uniform. It will stay uniform until the end. Okay. So, and again, we can show that on elevation, cross section, or we can show it on a plan view. Please take your time and look at both the elevation to the left and the plan view on the right on how do we show the snow drift diagram on both the cross section on the left and the plan view on the right. Let me check how you guys are doing so far. How are you doing so far? I'm asking you, how are you doing so far? Lost? Too much? Very intense? Very difficult? I'm not getting any feedback. Do you hear me? I cannot see you, so I don't know whether you're listening or that there's a problem with my internet.
Yeah,
So
I can hear you.
Hey,
Excuse me?
Yeah, we can hear you. It's going pretty good so far. It's like somewhat
It's kind of
confusing, but I guess
confusing,
after practice we'll get it.
Guys, I put a lot of effort to produce those slides, and I'm hoping those slides, they are highlighted. And again, that's from my perspective. I could be wrong. I could be, maybe my slides are the worst, but I'm saying I'm trying to do my best to make my slides as clear as I could. Okay?
It's good. We will learn best from doing. You know.
Of course, that's Michael, right?
Yes.
Okay, perfect. So, of course, I agree 100% with Michael. If you stay here as witness and, you know, as a watching me, yeah, maybe, okay, maybe, yeah, that's great. But really, you will learn when you do it by yourself. And this is, again, I gave you complete numerical example, and simply in the assignment, you will see kind of a very similar problem where maybe I change the location, maybe I change some of the heights of the parapet, just to train you on, it's not going to be 100% identical, because that's really bad for you, not bad for me, okay? Anyway, so for now, I'm going to assume that you guys are following and you have no problem. As Michael said, nothing is easy. In order for you to learn, you must be in pain. You have to, print the slides, or maybe look at it online, hide it, and try to do the calculation, go back and see what did I do here and there. That's the only way you can learn. Otherwise, if you say, okay, Tahir is making easy, or the question is easy, and you try to do it on the exam, on the assignment, on real life, you cannot do that. You have to do it yourself. Okay, now, a complete example by numbers for the snowdrift, and I need to remind you, you can see after all this pain and all those numbers, I'm able to find the snow diagram only on the lower roof. If you want to find the snow drift on the higher roof, then is not the same, because on the upper roof, there is a uniform for sure away from the parapet, but as you go close to the parapet from every side, from each side, then there will be a snow accumulation. But remember, the way we estimate the snow accumulation for the parapet is not the same as the snow accumulation from the multi-level. A multi-level is more complicated. You have to do case 1, case 2, case number 3. For parapet is very simple, same as this here, okay? Same as this one here, okay? So anyway, we have 10 minutes for our class, and really what I want to do is this thing here. So need to remind you, what if I have a higher roof and we have adjacent lower roof, and the distance is more than 5 meters? What do you think? More than 5 meters, it means, thank you, the lower roof will not be affected at all by the higher roof. There is no drift from the higher roof. If the distance is 0, you know what to do. So if the distance is 0, we already solve it. So what if I have a distance of 2.5, for example? What if the distance is 2.5 meters? So I have a higher roof and I have a lower roof, and then the distance is 2.5 meters. What can you do? Here is the answer. And the answer is in this slide. So if the distance is 2.5 meters, okay, or 2 meters, or whatever the distance, let's make it simple. I'll go back to my problem. So here, the XD is 3 meters. Huh? So let's say I have two buildings, and the distance is 1.5, only 1.5. So half of 3. The way we solve this problem, it doesn't, for 99% of the solution, doesn't change from what you've seen so far. You will do case 1 and case 2 and case 3 if they're applicable, and I will talk about the applicability soon if there is time, if not next class. But you will have to repeat what I did in my class today. When the time comes to place, your diagram on the cross section, you can see on my screen here there are some dashed line. So you will place your diagram whatever your diagram is. For example, your drift is 3 meters. Okay, if your drift is 3 meters and the distance is more than 3 meters, it means nothing, right? If your drift distance is 3 meters and your building is more than 3 meters away, between 3 and 5, then nothing, right? Because simply you will be in the uniform part. However, if your drift distance is 3 meters and then the separation between the building is 1.5, so what does it mean? It means mathematically you just have to draw exactly the same diagram here. However, you can see things will start from the higher roof. However, this part is dashed. Why dashed? Because simply all this snow will fall to the ground, and you only left with this part of a small part on the roof. You know what? I know that you guys don't see my cursor, so I'm going to stop presentation, and I think I'm not going to do that again. However, what I will do is I'm going to show with you guys my desktop. And I will just quickly go to Guys, do you see my cursor now? Do you see my cursor now?
Yeah, we
Yes.
can see it.
Yes.
Perfect. Look at this. So again, one more time, I know it's very hard to kind of imagine, and maybe that's very distracting to just keep imagining, but here we go. Here is my cursor. What I'm saying is, if you have two buildings, the red buildings, one is high, one is low, and let's say the distance is 1.5 meter. It is 1.5. If it is more than 1.5, more than 5 meter, then no effect. If it's in between 0 and 5, that's what you should supposed to do. Let's take the example where XD is equal to 3 meter. So you can see 3 meter XD from here to the end of the drift is 3 meter. And the actual separation is 1.5. Guess what? All you have to do is start from the higher building and then draw your diagram. Draw your diagram. However, the part in between, just imaginary, it will fall onto the ground. And you're only left with this part here. Okay? And I guess you can just find by math. Huh? Remember, if the same problem before, this will be 1 kVA, this will be 1 kVA, and if I go back, this was 2.59. So this value from here to there is 2.59. So let's say for simplicity, let's make it 2.6. So this 2.6 and this one. So I have here for the triangle, I have a 1.6. And because the distance is 1.5 and XD is 3, then this distance is equal to 1.6 divided by 2. So we have 0.8. So guys, my diagram will be in blue, will be 1.8 at the edge of the lower building, and then it will go in 1.5 meter, will go to 1 kVA. So conclusion is, if you get two buildings with a separation in between, if the separation is more than 5, thank you, there is no effect. If the separation is less than XD, then what you'll get, only the portion of the diagram will remain on the building. So what you do is do all calculation normally, and then plot your diagram, and then anything in between, you have to dash it. It doesn't exist. And using geometry, you can simply find what should be the load intensity at the edge of the lower building using math. Okay? I guess I'm not gonna, push hard. Probably I'm going to continue on this presentation next class. For now, guys, do you have any question for me? Do you have any question for me? Now, if you have no question, so guys, listen, I wanna say something. So you can see assignment number 2 is already published on the D2L. Again, don't be so excited, get so excited, because look at the deadline. The deadline was set to sometime in October, I think next Wednesday. So today is Monday, so I guess it's 10 days from now. Again, why I'm giving you or releasing my assignment early, there is a little part by now you cannot solve, very little at the very end. By now, you can solve probably 90% of your assignment, 90%. And I release it so early, so I give you more time to work on it. Because simply the assignment will cover live load. You know what's live load and how can you find dead load, and then snow load, and then the drift as well. So by now you should be able to finish 90% of the assignment. There is a very little portion of the assignment, very little, I would say less than even 5%, okay, about the rain, about the bonding diagram, which we will cover next class on Wednesday. And as I mentioned, my promise for you always, there will be a 1 week to solve the assignment, 1 week, which means if I finish early next class by Wednesday, the rain load, then you have your week to solve it. But again, it's more than 1 week, because practically you can start right now to solve, and you can finish 90% or 95% of the assignment. Okay? And as I said, please work hard, work on time, manage your time, and don't leave things to the very last moment. Any question for me? Okay. Thank you so much, and I will see you guys on Wednesday, 4 hours. Have a good day. Thank you, sir. Thank you for all of you. Thank you.